Okay. Now, in this lecture, now we will continue on our understanding of the role of chloroform. It was invented in 1931, if you recall, and soon after the invention, the number of refrigerators and increased rapidly in United States, and both CFC1 called Freon 11 and Freon 12, both were rapidly produced in hundreds of thousands of tons. So by the 70s, these were being released in the atmosphere in large amounts. Okay. Now, this happened because these chemicals were used not only in refrigerators air conditioners, they are used as sterilization in medical application, as foam products, as aerosols in containers which all of us use, and for firefighting, halons are used in as way to control fire, as solvent cleaning products. Okay. So you can see that number of the so-called harmless chemicals were used in the 30s, 40s and onwards, and they were non-toxic, non-flammable, and didn't have an odor and non-reactive, so they thought they were safe. But these accumulate in the atmosphere because they are a long lifetime. Okay. The long lifetime is what you should remember. Any new chemical you put in the Earth's atmosphere has a long lifetime, has a potential to damage the Earth's climate and chemistry. Okay. Now, this graph shows increase in production of Freon 11 beyond 1958. Ultimately, it reached 20 million metric tons. From hundreds of thousand tons, we went on generating more and more. So, by 93, where the ozone hole problem became very severe, we are producing 20 million metric tons. Okay. So, the Montreal Protocol had to do a lot of drastic measures to bring down this huge production, which was around 20 million metric tons, to almost zero by 2010. So, this was a major achievement, for which you have to give credit to all the countries in the world which realized the serious mistake they had made, and within a matter of 20 years they brought it down to zero. Okay. So, here is an example of various chemicals which were produced, which were ozone depleting substances, and some of the most reactive were chlorine monoxide, bromine monoxide, bromine atoms, chlorine atoms, which came out of these chemicals. Okay. These chemicals were non-reactive in the beginning, but when they went to stratosphere, the high energy ultraviolet photon broke these bonds and created all these chemicals, chlorine oxide, bromine oxide and so on. So, the depletion of stratospheric ozone is shown here from 1980 rapidly to 1995. It was depleting very rapidly, you can see. And even after the Montreal Protocol was signed, the ozone amount did not increase, it remained very low. Okay. That is because this phenomenon in the Earth's atmosphere have a long time scale. You start producing ozone today, you start producing these chemicals today, it will not immediately control ozone depletion, because chemicals were released last year, 10 years ago, 20 years ago are still around, and they go and attack the ozone layer. So, it took a long time. We still have not completely out of the woods. We have stopped further release of all these chemicals, but the ozone is not been restored to the value which was there in 1980 yet. It will take some more time. Okay. So, the role of chlorine was demonstrated very nicely when aircraft was taken to Antarctica, and aircraft showed clearly that when the amount of radioactive chlorine increased rapidly with latitude here as you approach the Antarctic region, the ozone layer depleted. So, this showed a clear link between ozone depletion and chlorine. Okay. Before that, people had certain doubts, but once this aircraft measurement showed clearly the connection between chlorine oxide and ozone depletion, the true mechanism which caused a large depletion of ozone was clear. Okay. Now, you must remember that the low stratosphere in the Earth's atmosphere also controls the amount of ozone in the stratosphere. When the stratosphere is very cold, there is very low ozone, about 150,000 units. When the stratosphere is very hot, it's more like 400. Okay, huge difference. Okay. So, if stratosphere starts cooling, ozone will start depleting. So, if you just recall what I discussed in the last lecture, because of global warming, stratosphere is cooling. Because of the release, because of the increase in the carbon dioxide, the stratosphere is cooling, troposphere is warming. If stratosphere is cooling, then ozone will get depleted. So, now you see the connection between ozone depletion and climate change. Climate change causes the cooling of the stratosphere, which will increase the ozone depletion. So, today you have to control the cooling of the stratosphere by reducing the CO2 emission, because CO2 increase in the stratosphere causes the cooling, which leads to the depletion of the ozone. And you can see when temperature is very, very low, like minus 75 degrees centigrade, the ozone amount is almost less than half of what it is when it is around minus 60. Okay. A 15-degree drop in temperature causes ozone to become half. So, that is a very serious issue. So, remember that this depletion does not occur throughout the year, because there is no sunlight in Antarctica in Antarctic winter. Okay. So, for ozone depletion to occur, the Antarctic region must have sunlight. That means Antarctic must be in its summer period, and then the sunlight has to be there, and these ozone depleting chemicals like chlorofluorocarbon must be there and should have created chlorine oxide. So, chlorine oxide and the presence of clouds in the stratosphere and the sunlight, three things are required. You need sunlight to split the chlorofluorocarbon to create chlorine, and this chlorine will attack the ozone molecule. So, sunlight is required, and you need these clouds to accelerate the reaction. So, the combination of sunlight, the presence of clouds and chlorine gas occurs only for a short period during the spring of the stratosphere around September, October. Okay. So, maximum depletion occurs in September, October. Then once there is no sunlight in stratosphere in its winter, then nothing will happen for the next 6 months. Then again, when the sunlight comes, there will be depletion of the ozone layer. Now, although Montreal Protocol was signed in 1987, you can see the size of the ozone hole defined by the region where the ozone amount is less than 220 Dobson units. The ozone layer has not decreased. It has a size of radius of 25 kilometers between 1993 and 2001. So, because of the presence of chlorofluorocarbon, the ozone hole continued to increase in size between 1993 and 2000, although we had reduced the release of chlorofluorocarbon, but because these substances have a long lifetime in the Earth's atmosphere, thousands of years, so just because you stop releasing these chemicals, their amount will not be reduced, they will take time. So only in the last 10 years we see a depletion in the chlorofluorocarbon, and it will take a long time for the ozone to reach the level that were there before 1980. Okay. Now, just to point out that the hole in the Antarctic layer in Antarctica was dramatic, but there is also ozone depletion in the Arctic, okay, but it is much smaller, okay, and it is not as extensive as that in Antarctica, because the ozone in the Arctic, when it is depleted, is able to mix with ozone from other regions, and that ozone mixes with the ozone from Antarctic and alters the amount of ozone in the Arctic. So, Arctic has a benefit of interacting with the surrounding atmosphere, which is not there in Antarctic because of the closed vortex. Okay. Now, what this graph shows is ozone on the left and chlorine oxide on the right. Wherever chlorine oxide is there, ozone is depleted. So, a very clear demonstration of the connection between chlorine oxide and ozone. And this is shown again in the graph as the depletion of the ozone in Antarctic in October and Arctic in March. Remember, in March is the spring in the Arctic. That is why combination of sunlight, chlorine oxide and temperature cause the destruction of ozone. So, the ozone destruction occurs in different months in Arctic and Antarctic, because you need sunlight and you need chlorine oxide for this to occur. Okay, just to remind you again that ozone depleting substances are used in a wide variety of applications by human beings as refrigerants, as foams, as cleaning solvent, as propellant for aerosols, fire extinguishers, fumigants, chemical synthesis feedbacks, as a sterilization for health products and various laboratory uses. Okay. So, we have to now cut down all these applications and find new chemicals which do not harm the Earth's environment. Okay. So, the primary source of chlorine are mentioned here, various examples. These are entirely human made, they do not occur in nature. Now, since there are many chemicals which are leading to ozone depletion, it is important to compare all these chemicals, which is less restrictive. So, for that the United Nations came up with a criteria called ozone depleting potential, which means the potential of a given chemical to deplete ozone when compared to Freon 11. Freon 11 is our reference gas, CFC11, chlorofluorocarbon, and we compare all the other molecules which cause ozone depletion with CFC11. And this is the way these treaties operate. We have a convenience a reference gas, and we compare all the gases with reference gas and then decide how to control these. So, this is the reason because all CFC are not equal. Okay. For example, if the ozone depleting potential of CFC11 is defined as 1 because it is a reference gas, then HFCs, hydrofluorocarbons, have 0 ODP because they do not contain chlorine. Okay. So, HFCs became very popular for use in refrigerators because they don't cause ozone depletion. Okay? Because their ozone depleting potential is much lower than that of CFCs. So, as far as ozone depletion is concerned, we want to choose a chemical whose ODP is below 0.1. Okay? And that is where the challenge is there. So, here is an example of chlorine and bromine gases used in the Earth's atmosphere. And so, you can see that there are many sources for ozone depletion, both bromine and chlorine. They had to handle them to control the ozone layer. The ultimate objective of the Montreal Protocol was the elimination on the basis of certain knowledge, elimination of the chemicals which cause the okay. Now let me show you how the change in ozone, okay, increases the amount of ultraviolet radiation that is there in the south pole of Antarctica. Okay. If there is no depletion of ozone, then there is no reduction, increase in UV. But as the ozone depletion occurs, moving from right to left, the ozone depletion goes up by 1.5 times. Okay. So, this shows a clear connection between ozone and the ultraviolet radiation which comes into Antarctica. Okay. Skin cancer, sunburn, eye damage, cataracts can occur, will reduce by 10% for a 20% increase in, and can cause 20% increase in skin cancer if you reduce the ozone layer by 10%. Since ozone layer affects the DNA of human beings, you need to be very careful about this particular gas. So, Montreal Protocol said 50% cuts on these 5 chlorofluorocarbons and 3 halogens by 2000, which was a very drastic measure because the protocol came into play only in 1990 or so, and within 10 to 20 years you have to reduce all these chemicals. So, as the discovery of more deadly chemicals were made, the Montreal Protocol went on changing the conditions imposed on the various chemicals. Okay. So, more and more chemicals are added and more stringent measures were made to control these chemicals. So, this figure shows how chlorine concentration would have continuously gone up from 1990 to 2030 by a factor of 3 or 4 if the phase out had not been ordered in 1987. Because of the phase out, we have reduced the chlorine concentration in the Antarctic region. So, but still remember the ozone hole has not disappeared, it will take time, but chlorine concentration has been brought down. To point out how tough these negotiations were, starting in 1987, series of amendments were introduced into the Montreal Protocol in 1990, 92, 97, 99, 2007 and 2016 to ensure that we bring down the ozone depleting chemicals rapidly. Okay? Because as the science developed, more information came, more stringent regulations were imposed. And this shows how the total chlorine has been brought down in Antarctica after year 2000. It is going on this line, while it would have gone on along these lines if we had not done anything. There is no Montreal Protocol, the amount of CFC would have gone up rapidly to around the amount of chlorine in the stratosphere would have gone up rapidly to 30, which would have been very, very serious. So this shows the simulation that the Dobson units in the stratosphere of ozone would have gone down if you had not implemented the Montreal Protocol. Okay? Because of the protocol, we are able to maintain the ozone depleting substance reasonably constant. There are yet a variation due to natural factors, but we would have prevented this loss which has occurred now. Here is an example of how the chlorine level has gone down along with this reduction in the production of CFC 12, CFC 13, and these three agree with that. That shows that this protocol has been successful and bringing down the CO2, bringing down the chlorine in the stratosphere, and it will take some more time before we can totally control it. And three gases which are monitored, they are all now declining. Here is another example of how the various chemicals are declining. One chemical, HCFC, is not declining because at that time it was not realized that although HCFC is a good chemical for preventing ozone depletion, it happens to have an impact on global warming. Okay? When this was realized, further changes were made to the Montreal Protocol to make sure that this chemical also starts declining. And this chemical should decline because of its impact on the greenhouse effect. Okay? So in 1986, the share of the developed countries is only 5%. Okay? By 2002, it has gone up to 72%. So developed countries were producing more and more CFCs, and in the case of halons, which is used for fire protection, went up to 100%. Okay? So this clearly required new action. So developing countries also had to join seriously the Montreal Protocol, and so this was done in the years. Now in the next lecture I will talk about ozone depletion potential, a new metric developed to decide how to control the various gases in the stratosphere. Thank you.